Okay, we're going to continue our journey into techniques of integration. We looked at integration by parts previously, which basically dealt with essentially undoing the product rule and the quotient rule to some extent. Very useful technique. Now we want to turn our focus to integrals involving trigonometric functions, and that's a big area really. We're going to focus on particular forms. In particular, you can see the first forms we're going to mainly be concerned with are integrals involving products of powers of sine and cosine. Okay, if we have products that have other trig functions, remember that we can express all the other trig functions in terms of sine and cosine, right? Secant is 1 over cosine, sine, or cosecant is 1 over sine, and tangent sine over cosine, and so on. So, a lot of times this is a good starting point. Now, just want to remind you of these trig identities. You should be familiar with certainly the Pythagorean Pythagorean identities, and we'll be making use of these. Double angle identities actually come into play from time to time, and we'll see that. And so especially this one here involving sine of 2x is 2 times the sine of x times the cosine of x. This is proved from the sum identity for sine, if you remember from trigonometry. And then also these power reducing formulas, and we're going to make use of these in our first example. So the first example is to evaluate this integral here using a trigonometric identity. Now you might think, hey, we don't need one because I know the antiderivative of sine of x is what? Negative cosine of x. So isn't the antiderivative of sine squared x just negative cosine squared x, or maybe positive cosine squared x? What is it? It's neither one. If I took the derivative of cosine squared by the chain rule, right, I'd have to bring the 2 down times the cosine of x times what? The derivative of cosine x, right, which is negative sine x. And so I don't get sine squared x, okay, if I take the derivative of cosine squared x or negative cosine squared x. So you can't just do that. That's not valid. So how do I do this? You might think, well, I can use integration by parts because it's sine squared x is really sine x times sine x, but we don't want to do that. It's not going to be helpful, right? Integration by parts will not work there in that case. Well, if we look at our trig identities, clearly we see 2 that have sine squared x. We see the Pythagorean identity, and we see this power reducing formula. Pythagorean identity is not going to work. If I solve for sine squared x, that's 1 minus cosine squared x. I'm exchanging the integral of sine squared x for an integral involving cosine squared x. That gets me nowhere. However, this one, I can replace sine squared x with what? Just cosine of 2x, cosine to the first power. Notice that is just a simple composition, and we're going to be able to use a u substitution to make use of that. So I'm going to make use of this identity here for this first one. So I'm going to simply rewrite sine squared x as 1/2 1 minus cosine of 2x. Remember, this 2 can't come out. It's cosine of 2x. It's inside the cosine function. So that's a composition. But notice I can do a substitution now very simply, letting u be 2x, right? And then what is du in that case? Well, du is 2 dx. Okay. Now I guess I have a 1/2 dx. So if I multiply both sides by 1/4, 1/4 times 2 is 2/4, which is 1/2 dx. And using this information, I can rewrite this integral. So the 1/2 dx becomes 1/4 du, and I'll go ahead and pull that 1/4 out, du. And then I've got 1 minus cosine u. Okay, so 1 minus cosine of 2x, u is 2x, so 1 minus cosine of u. And then the 1/2 times dx becomes 1/4 times du. And now I can find the antiderivative. I have a constant multiple here. Again, with respect to u now, right, our new variable, what's the antiderivative of 1? That is u, right? And the variable is u. What's the antiderivative of cosine u? Sine u. Okay. And now I can throw in my plus c. Of course, I want to go back to the original variable, so I'm going to replace u with what? 2x. And so I get 1/4 u is 2x minus sine of 2x. And if I distribute that 1/4 through, right, make sure you distribute through, I get 1/4 times 2, 2/4, which is 1/2 x minus 1/4 sine of 2x plus c. And here is the antiderivative for sine squared x. And I would challenge you, take the derivative of this. This one's easy, right? Here involves a little simple chain rule. Take the derivative of this and see if you can get back to this expression here. Now you might have to go back and make use of one of these identities. Obviously, since we made an identity to go from here to here, we're probably going to get more back to this form when we take the derivative of this. And then we can rewrite it by, obviously, this identity back to sine squared x. Now, this is one form, but there's another form because, again, that's where it gets a little tricky. These trig identities, take a look at this double angle identity for sine of 2x. Notice we have a sine of 2x here. So if I make use of that and replace sine of 2x with 2 sine of x cosine of x, and 1/4 times 2 is 1/2, then we get this other form, I'll just say, which is 1/2 x minus 1/4 times 2 again is minus 1/2, the product sine of x cosine of x. So again, both of these are antiderivatives. They only differ by a constant, even though they look a little bit different there, right? They are essentially both antiderivatives, right? It's the same expression in a sense because of that identity. So, you know, and you can check again, take the derivative of this and see if you can get back to sine squared x. Okay, again, you might have to use some trig identities to get there. Okay, all right, so I've done this for the antiderivative for sine squared x. Do you think we can similarly do the antiderivative of cosine squared x? Yeah, right here. And look at the relationship between these two identities. Sine squared x is 1/2 1 minus cosine 2x. Cosine squared x is 1/2 1 plus cosine 2x. So plus, you can almost see, you know, what's going to be different. They're going to be essentially the same, right? So I want you to similarly do the integral of cosine squared x. Make sure you do that one. Okay. I might ask you on a test or quiz to do that, given these you know, power reducing formulas, which again, these are all on that algebra trig review sheet that I give you during tests or quizzes if you need it. Okay. Now so we know the antiderivative of sine of x, right? That is going to be cosine of x. We now know the antiderivative of sine squared x, right? Which is one of these. And now we're going to go to sine cubed x. So how are we going to do that? Well, this is going to illustrate a technique that we're going to use. What I'm going to do here, again, there's no direct trig identity with sine cubed x that we have in our list. But what I'm going to do is I'm going to peel off, if you will, one sine x factor. So sine squared times sine x is sine cubed x. I want to peel off a sine of x, and the reason I want to peel it off is I'm going to peel it off for the du. Okay, I want this to be essentially a multiple of du. And what do I mean by that? I'm going to actually choose u here to be cosine x. Now you think I'm crazy. You say cosine x. There is no cosine x here. Why in the world would I choose that? There's sine x and sine x and sine x. That's all we have. Well, let's go back to our trig identities. And we have sine squared x again here, and we used a trig identity for that here. And certainly you can see, where we have a cosine on this side, but I'm actually going to make use of the Pythagorean identity this time. Sine squared x is equal to what? 1 minus cosine squared x. And so that's what I'm going to do. I'm going to write this as 1 minus cosine squared x, right? And so that's by the Pythagorean identity. I'll abbreviate that. Pythagorean identity. And so that's what we're going to do. So notice that this becomes, with this u, let's see, what is our du? We always need our du. What's the derivative of cosine x? So be careful. We got antiderivatives and derivatives. When we take the derivative of cosine of x, we get negative sine of x. Okay, and so there's my sine of x dx. I just need to multiply both sides by -1. And so sine of x dx is negative du. And 1 minus cosine squared x is what? 1 minus u squared. So this becomes 1 minus u squared. And the sine x dx, right, this becomes our negative du. Okay, so I can distribute this -1 through, and I get the integral of, actually I'll just pull that negative out here. Pull that -1 out, and I'll be left with 1 minus u squared du. I can distribute it through -1 plus u squared. That's fine. But now I know how to find the antiderivative of this, right? This is just antiderivative of 1 with respect to u again. Don't forget we got this minus sign out here, is u. And then the antiderivative of u squared by the power rule is what? 1/3 u cubed. Right? And now I'll go ahead and distribute that negative sign through. I could have done it to begin with. And I'm not done yet because I've got to replace u with what? Cosine x. And so what do I get? I get negative u, or negative cosine of x, minus plus 1/3 cosine of x cubed, and we usually write that as what? Cosine cubed x. And there is our antiderivative. But this is the technique we're going to use when we're finding integrals involving products of sine and cosine. We're going to peel off, if there's an odd power of sine, we can peel off one of the signs, and that becomes our du with our u equal cosine x. The even powers of sine, we're going to be able to convert to cosines by the Pythagorean identity. Similarly, if we have an odd power of cosine, we'll pull off one of the cosine factors for the du, and we'll do u as sine of x, and we'll convert all the powers of cosine to sine by the Pythagorean identity. And that's the technique that we're going to use. So this next page shows the general strategy. Now, let me jump here first of all. So if the power of sine is odd and positive, we're going to save one sine factor for the du, and we're going to convert the remaining factors to cosine by the Pythagorean identity. So if this is odd, I'm going to peel one of the signs off here for the du, and I've got sine squared. It might be sine to the 4th, and then I can do sine squared squared, or it could be sine to the 6th, which would be sine squared cubed, right? Or sine squared to the 4th is sine to the 8th, and so on. So this sine squared, then I can convert the cosines, right? We know this is 1 minus cosine squared x here, and then of course I might have to expand that out, right? But I'll be able to do that integral as just with just the power rule and just those basic rules. If the power of cosine is odd and positive, similarly we'll pull that cosine x factor out, so So we'll have an even number of cosine powers, and we'll convert those to sines by the Pythagorean identity. And this cosine x dx will be our du. So if one of our sines or cosines is odd, that's good. Now what if it's not? Well, if they're both even and non-negative, then we've got some work to do. I want to remind you that we proved with the integration by parts this integral power reducing formula for sine. All right, takes a integral involving the nth power of sine, and we end up with an integral involving n minus 2 power of sine, right? So it reduces the power. And if I don't know how to do this integral, this power of sine, I can plug it back in here and continue to get till I can get to an integral I can do. And we have a similarly this power reducing integral formula for powers of cosine. Okay, so if both powers of sine and cosine are even, then what we can do is we take the smaller power. Okay, say the sines are the smaller power. M is the power of sine, n is the power of cosine. If m is less than or equal to n, I'll convert all the sines to cosine. Okay, and then right, everything's going to be powers of cosine. I expand this out, right? I'll expand this out, and I will be able then to use the power reducing formula to solve those. On the other hand, if m is greater than n, we'll do it instead. We'll replace the cosines with sines by the Pythagorean identity, and then we'll use the power reducing formula for sine. That's one way to do it. There is an alternative way to do it. You can make repeated use of these identities to convert the integral to odd powers of cosine, and then expand as a sum of integrals involving smaller powers of sine and cosine in the variable 2x. So there's lots of other ways to do this. The book illustrates, I think, both of these ways. I'll mainly focus on this first way with one example. Okay. Bottom line is, if one of the powers is odd, we don't have to go here. Okay. If they're both even, then we're we have to go here. So let's take a look real quick at these and illustrate that. So that was a bunch of hard to follow stuff maybe, but now let's make it clear what we're going to do here. Take a look at this. What do we have? Do we have an odd power of sine or cosine? That's the question. Yes, we do. So I'm going to peel off the cosine, one of the cosine x's. As long as we got an odd power of sine or cosine, we're in business. So right, this becomes cosine squared times cosine x. So this I'm going to save for the du. That's going to be for my du. Okay. This I'm going to convert to, right, sines by the Pythagorean identity. 1 minus sine squared x, right? Cosine squared x plus sine squared x is 1. And so cosine squared x is 1 minus sine squared x. So I'm going to let u be sine of x in this case. If I have an odd number of cosines, I'm going to let u be sine of x. So my du, what's the derivative of sine of x? Cosine of x. All right? And so there exactly is my du, right? The cosine x dx. And so with that, this integral becomes the integral sine squared, sine of x is u, so that's u squared, times cosine squared x, which is 1 minus sine squared x, so 1 minus u squared, and cosine x dx is du. Okay, see how that works? Beautiful. Now, before I do anything, I must distribute this through. You can't find the antiderivative of this and antiderivative of this and multiply them, right? Please don't do that. We simply expand this out. I get u squared minus what? 2 plus 2u to the 4th. And now that's easy. The antiderivative of u squared is 1/3 u cubed minus 1/5 u to the 5th plus c. And lastly, we go back to the original variable. Sine of x is u, so I get 1/3 sine cubed x minus 1/5 sine the 5th x. Not bad. Not bad at all. Let's try another one. The one down here, do we have an odd power of sine or cosine? Here we had an odd power of cosine. Here we have an odd power of sine. So what are we going to do? We're going to peel off one of those signs for the du. So this will be leaving me sine to the fourth x, cosine the fourth x, sine of x dx. I'll pull it over here. Now, when I come in and I'd say let u be cosine of x right now, that's what we're going to choose in this case. So that our du, though, notice derivative of cosine is negative sine x dx. So we do have this little negative factor floating around to remember that we have to be careful about. So this part right here becomes negative du. Okay. Now, of course, this will just be cosine to the fourth is just u to the fourth. Now, what about this sine the fourth of x, right? Well, this is the same as sine squared of x squared. Do you see that? So if it's a even power greater than 2, I'm going to write it as sine squared x to some power. I can do it that way, which means sine squared x, again, in the parentheses, is 1 minus cosine squared x. Okay. And so this becomes 1 minus u squared squared, right? Because u is cosine of x. And so what does my excuse me, integral become? 1 minus u squared squared u to the fourth, and then minus du. I'll pull that minus sign out here. Okay, so I've got some work to do. Let me expand. I have to expand this out. So this will take a little bit. Remember how we expand this out. It's 1 minus u squared times 1 minus u squared. So it becomes 1 times 1 is 1. The inner and outer is negative u squared, so it's a negative 2 u squared. And then negative u squared times negative u squared, positive u to the fourth. Okay, distributing this u to the fourth through gives me u to the fourth minus what? 4 plus 2 u to the sixth, u to the fourth times u to the fourth, u to the eighth. And if you want to distribute this negative sign through, you can. But now we're ready to do the antiderivative, so I'll go ahead and distribute this negative sign through. So I got negative u to the fourth, so that's negative 1/5 u to the fifth, minus minus plus. So what's the antiderivative? 2 u to the sixth, that's 2/7 u to the seventh. Negative negative. The antiderivative of u to the eighth is 1/9 u to the ninth plus our c. Okay. Finally, we go back to the original variable, which is cosine x. And there it is. So that's quite a masterpiece there. It's quite an amazing thing we can do there. We wouldn't in a million years have come up with that as the antiderivative for the original, right, function sine to the fifth x times cosine to the fourth x. Okay. All right, let's take a look at an example where we have even powers. So these are good. If we have an odd power, we peel one off and make that the du, and we're good to go. As long as we have one. If we have both odd powers, you can choose either one. Doesn't matter. You can go either path if they're both odd. But what if they're both even? So we'll finish this video with this one. What happens if they're both even? Okay. So here you would take the smaller power. Of course, they're both the same, and you would convert all the smaller powers. If the sine was smaller powers, you convert all the sines to cosines. If cosine was a smaller power, you'd convert them all to sines. So I'm just going to choose to convert the sine to cosines. Okay, so I'm going to say that sine squared x is 1 minus cosine squared x. convert all to cosines. So, and if it was, to the fourth, if it was sine to the fourth and cosine to the fourth, I can do this and square it, and I'd have to expand it out. But I can do this. In other words, this whole expression is going to be powers of cosine. In fact, if I distribute the cosine squared through, I get cosine squared x dx. And I'm going to split this up in two integrals, minus what? Cosine to the fourth. So I'm going to use the properties of integrals to break this up, right? The linearity properties here. And so it's going to be the integral of cosine squared x minus cosine to the fourth x. And I break it up into two separate integrals. And now what I'm going to do is I'm going to use the power reduction formulas for cosine. And really, this is the integral, I should say, integral power reducing formula for cosine. So let me just pull those out. So now I'm not talking about the power reducing formula for cosine squared x. I'm talking about the integral formula right here. We'll put that up at the top. Okay. So now I can do these, right? For this one is with n equal 2. And what does that give me? When n is 2, cosine squared x is what? 1 over 2. Cosine of 2 minus 1 is 1, so that's just cosine to the first power, sine of x. And then n is 2, I get 2 minus 1 is 1/1/2. And then cosine, what? N is 2, 2 minus 2 is 0. What's cosine to the 0 power? What's cosine to the 0 power, by the way? Answer, 1. Okay, we interpret that to be 1. So it's just 1 here. 1, what? Just 1 dx, right? And what's the antiderivative of 1? This is going to be just x, right? That's just going to be x. So that's our first integral. And now what's our second one? Minus, now n is 4 here. So go back up to that formula up there. Make sure you can see it at the top. When n is 4, I'll have 1/4 cosine 4 minus 1 cubed x sine of x. So that's that first part. N is 4. 4 minus 1 is 3/4. Integral cosine of 4 minus 2 is 2 cosine squared x dx. Well, now we have to integrate cosine squared x, but we just did that, right, with the formula. And so we're going to replace all of this, right, with what we have here. Okay, so let's write this out and see what this looks like now. This is 1/2 cosine x sine x plus 1/2 x. Now there's a plus c, but I'm going to put it at the end when I'm done with everything. I'll combine all the constants in as one big constant. Okay, so here I've got minus, be careful, minus 1/4 cosine cubed x sine of x minus 3/4 times the integral of this thing. And what's the integral of this thing? So that's all this stuff here. That's this stuff here. So that's going to be 1/2 cosine x sine of x plus 1/2 x. All right, so that's all this stuff comes from what we just did over here. Does that make sense? Kind of, and you can see if we have higher powers, cosine to 6th, we're going to end up with a cosine 4th. Well, we would have done that if we did the cosine the 4th, or we could do it, right? And we can plug that in. So it's kind of a nested procedure, the higher the power. Okay. And so if I distribute this through, notice I'll get negative 3/4 times half, negative 3/8 times this, and negative what? 3/8 x. Okay, and then I can combine some like terms. So I've got 1/2 cosine x sine x minus 3/8. 1/2 is 4/8. 4/8 minus 3/8. is 1/8. I've got 1/2 x minus 3/8 x. 4/8 minus 3/8 is 1/8 x. And then I also have this right here, minus 1/4. Oh, and by the way, finally what? Plus c. I could put a plus c, up here as well, I guess. But and when we're all done, we'll stick in the plus c, knowing that we can have any constant. Okay, so you can see that's a little bit of a process, a little bit algebra intense. You've got these nested expressions. Got to be careful about distributing things through, especially if they're very high powered. This is just second power. So if we've got fourth power, you're going to be squaring this thing. You're going to get more integrals to do, and it's just going to be harder and harder. So obviously, if you have something like sine to the 8th and cosine to the 10th, you're in for a long journey. Okay, but that's the idea. Okay, so we are done now focusing on sine and cosine. In the next video, we're going to turn our attention to products involving secant and tangent.